Hello, this is MA280 Multivariable Calculus. I'm Professor Wheatley. Our topic today is going to be one of two methods for multiplying vectors together. Dot product will be our topic today. We'll discuss a cross product in the future. So, definition. The dot product between vectors u and v, and let's say u is components x1, y1, z1, v is components x2, y2, z2, is u dot v, sum of x1, x2, y1, y2, z1, z2. So there is the dot product, and this is read just like I said it. This is u dot v. So we don't really use the traditional times there because there is no single vector multiplication operation. There's more than one way of doing it depending on what you want to accomplish. So this is u dot v. There are a couple different names for this. A dot product is synonymous with a scalar product. The reason there being that this is not a vector, so you've lost all indication of I, J, and K. So you have a scalar that comes out of here, scalar product. It is also the inner product. We won't refer to that too much, but if you take something in linear algebra and you talk about spaces, vector spaces, inner product becomes an important idea of measuring angles between things. And in fact, we're going to talk about that shortly, this idea of angles. But we will mostly refer to it as dot product. Brief example here to just show algebraically how things go. If I have some vector minus 2/3 I plus k, and I dot it with negative I minus 2j plus 3k, notice I'm working in 3 space here. It doesn't make a difference. The dot product is completely analogous for any dimensional space, 2D space, or anything you want. There's no difference. This is in a sharp contrast to the cross product, which we'll see in the future. This winds up being minus 2/3 times minus 1 plus 0 times minus 2 plus 1 times 3, and that is 2/3 plus 3, which is 11/3. That is your dot product. So there is algebraic example of that. Let me now go to an idea of why I want to use this. And again, I mentioned that the inner product was some way of generalizing the notion of angles between two vectors in a vector space, an arbitrary vector space. We can make that very concrete when our vectors are in 3 space or 2 space. So let me come over here, and let's take so alternate view. So if you have 2 non-zero vectors, u and v, x2, y2, z2, u, v, not the 0 vector, right? And you can place them so their initial points coincide. So I can have something like that. Right, so initial points of u and v are coinciding here. They come together at a point. There's clearly an angle between those 2 vectors. And this is a 2D drawing, but I mean, if it's in 3 space, I mean, simply imagine it being off the board. It has no bearing on the picture. So you have an angle theta in there, right? And we can make the restriction on theta between 0 and pi. If it was the other way around, we could just reverse the positions of u and v to make this restriction okay. So this is nothing major. It just keeps us from having to worry about repeating values of the cosine inverse function. All right? It turns out that theta is the cosine inverse of u dot v over magnitude of u times magnitude of v as such. Right? So theta is the cosine inverse, and that's why we have to restrict it up here. Cosine inverse is only its range is 0 to pi. We can only get angles like that, right? And so what this leads us to is, since we have this restriction, we can take the cosine of both sides of that equation, have it be well defined, and we wind up with u dot v equals magnitude of u, magnitude of v, cosine theta, like that, right? And so this is another way of viewing the dot product. It's probably not at all clear that these two are the same, but in fact, one could prove it without too much difficulty by using the law of cosines. You could see that these are equivalent. We will not do that, though. So let me use this idea to do a little bit of geometry and determine an angle between some vectors. So let's do an example here. Let's find theta in the triangle below. So let's see here. What do I want? So like that, and there, and let's do that. So let's call this point minus 1, 1, and let's call this 1, 0, and we'll call this down here 0, minus 2, and the angle in question is that angle right there, that theta. Okay. So what is theta? Theta is the angle between the two vectors, the vector AB and the vector AC, right? So there is AB and there is AC. Angle between AB and AC, right? And actually the order doesn't matter here. There's no orientation of this triangle. Doesn't make a difference. All right, so vector AB, right, is whatever, 0 to negative 1, so 0 minus 1, minus 2 minus 1. That ends up being 1 minus 3, right? That's that vector. And AC ends up being a 0 minus 1 and a 1. I'm sorry, I've botched this up. Wait, I've got my coordinates mixed up. 1 minus 1, excuse me, and 0 minus 1, and that ends up being 2 negative 1, right? And everything looks good there. Do I? Yes, okay. So now I can use this formula and get what I want to get out of this. So I need the dot product. So I need AB dot AC, right? Which is a 1 times 2 plus minus 3 times minus 1, which gives me 5, right? And I also need the lengths of these guys too. So I need a length of AB, right? And that ends up being square root 10. And length of AC ends up being square root 5, right? So now I have everything I need to do over here, right? So let me come down here. So theta is the cosine inverse of my dot product, 5 over root 10 root 5, right? That's root 50, which is root 25 times root 2. So this winds up being cosine inverse of 5 over root 25 times root 2, right? That's root 50 also. So the 5's will cancel. This will end up giving us cosine inverse of 1 over root 2, right? So now we're asking what is the angle between 0 and pi that has cosine 1 over root 2? We know it's pi over 4. Right, so this is a 45-degree angle here, pi over 4. Okay. So this can be useful in dealing with various problems of geometry. We'll find out that it has other uses down the road too, but these are some elementary ideas here. So the next idea comes from this definition of the dot product. What is often very useful to talk about in terms of vectors is when two vectors are perpendicular to each other. It turns out that orthogonality or perpendicularity, which is the same in 3 space, tends to lead to a lot of nice results, a lot of nice things depend on vectors being orthogonal to each other and orthogonal projections. We'll see what that means shortly. So let me talk about what it means for vectors to be perpendicular and how the dot product can play a role in that. So the definition, two non-zero vectors u and v are what we call orthogonal, and I will say synonymously here perpendicular, but that's not always true if the angle between them is pi over 2. The reason for the different notation here, the different language of orthogonal versus perpendicular, a perpendicular is a geometric notion that exists in Euclidean space. Orthogonal is a general notion that exists in a general vector space. And so you can have a vector space of things like functions, for example, where it doesn't make sense to say that functions are perpendicular to each other. That's not a geometric notion, but they are orthogonal if this angle between them is pi over 2. And so that's what leads to the idea that the inner product is a more general version of the dot product. Dot is inner product for R3 and R2, but inner is not always a dot product. And you could even talk about the notion of an angle between functions, then you get orthogonality, but we're not so concerned with that in this course. We're concerned with more concrete things. So for us, orthogonal, perpendicular, they mean the same thing. Orthogonal is perpendicular, perpendicular is orthogonal. Okay. Let's see what this means here. So take two vectors, u and v. They are orthogonal if and only if, that is to say, a two-way street, their dot product is 0. Right? So two vectors are orthogonal if and only their dot product is 0. Why? What's the reason? Let's take a look. So u and v, let's make the u look better. U and v are orthogonal definitionally if and only if the angle theta between them, between u and v, is pi over 2. Right? And if you think back to what the dot product was, remember we had the result that dot product was cosine theta times the magnitude of the vectors, right? So now we can say if and only if, let me skirt down here. Here is your dot product equals uv magnitude times cosine theta. If the angle between them is pi over 2, right, the cosine of pi over 2 is 0, right? So this term is 0 here. That means that regardless of what's going on over here, this entire piece will become 0, right? So this has a cosine theta equal to 0, right? And that's if and only if, because when theta is restricted between 0 and pi, this is pi over 2 is the only angle between these two values that produces a cosine of 0. And so that means if this is equal to 0, this must be equal to 0 also. Right, so u dot v is equal to 0. So there, what we have here is a very quick and easy test for orthogonality with the dot product. It's very convenient to be able to do that. Okay. So there's that. Some properties of the dot product. Let's talk about some of these. I said it was one way of multiplying vectors together. So our hope is it will carry some of the same properties that multiplication of real numbers carries. And in fact, we do get some of those, more so than the cross product gets another multiplication form. So let's talk about properties of the dot product. It's clear from the algebraic definition that the dot product is commutative. Commutative, right? Because multiplication of real numbers and addition are both commutative operations. That's certainly true. scalars distribute well over dot products. So you end up with, doesn't matter what order you put that scalar in there. You can put him in front of the u or in front of the v, or you can even have in front of the full dot product, and that will be true. So scalar multiplication distributes over dot products as we would expect it to. Okay? And the dot product, furthermore, is distributive over vector addition. In other words, if I have something like a u dot v plus w, this is u dot v plus u dot w. So this is distributive over plus for addition. Right? A useful property to have under your belt, if I dot a vector with itself, what do I get? Well, so think about it in terms of the components. Suppose u is x1, y1, right? I dot it with itself. I get x1 squared plus y1 squared, right? We know that the length of u is just the square root of that thing, right? So if I square the square root, I get back this u dot u. So in other words, this is the length of u squared, right? So u dot u is the length of u squared. That's handy to have under our belts. And last but not least, anybody dotted with the 0 vector is the scalar 0. Again, note that is the 0 vector, and this is the scalar 0. But this is all 0, so that should make sense. Anybody dotted with it is 0. Associativity, it's missing from this list, right? So commutativity is up here, distributivity, the other properties of multiplication that we're used to. Multiplication of reals is associative, but if I say something like that, so I have u dot quantity v dot w, right? It doesn't make any sense. V dot w is a scalar, right? So this is a scalar, right? This is still a vector, right? So vector dot scalar, not defined. And notice this is still a dot. This is not multiplication. Scalar times vector, great, no problem at all. But scalar dot vector, no good. Vector dot product is a vector operation. So this is not defined. So this is not associative. Not associative. That's not a big deal. Okay. So some basic properties here. Let's talk a little bit about an application of this, which is useful. I mentioned earlier that it's useful often to talk about vectors that are orthogonal to a given vector, perpendicular to a given vector. Let's see why that might be true. So let me turn to the topic of vector projections. So let's turn our attention to vector projections. This certainly has utility in a large variety of ways. We will look at one, and there are others down the way that we'll see as well, but certainly you can't get very far in engineering without considering vector projections, so they're in all kinds of places. Okay, here's a picture. Let's draw this so I get what I want. So let's label some points here. There's P and there's S, and up here let's put Q. And let's call this vector up here U, and let's call this vector down here. Actually, let me use a different color here. Let's use the black. So let's call this V there. Right? And so I'll start with a non-zero vector, V, which is PS in this case, and another non-zero vector U, excuse me, which is PQ. Okay? And I want to ask myself, what is the vector projection? Well, let me define it, and then we'll look at how we could think about it intuitively in terms of some real life stuff. So the vector projection of U onto V. So I'm being careful with my order of vectors here. U onto V is not the same as V onto U. They're different. And the denotation here is a little clunky, but it works. So we've got proj little sub VU. In other words, a U onto V. So you could think of it as big onto subscript, I think. It's a way to think about that. Denoted by proj sub V of U is the vector PR gotten by dropping a perpendicular. So dropping a perpendicular, that's what that is, from the tip of Q, i.e. the tip of vector U, onto the line through, or onto the line, I guess I want to say PS. Yeah. Yes, so notice that vector PS is finite length. I can run an entire line along here and call that line PS, and it will go on forever and ever. So there's the vector projection definition. It's the vector PR gotten by dropping a perpendicular from the tip of Q onto the line PS. Let me draw that up here in black. So if I drop a perpendicular, so I go perpendicular to the line PS, right? And then where I end up here, well, let me make this red so it'll look good. So this vector here, this is PR, right? This is the vector projection. This is proj sub V of U. Right? That is the vector projection. We dropped a perpendicular down from the tip of Q onto the line PS. And probably should preface this by saying that the perpendicular here I'm referring to is perpendicular to the line PS. It is not perpendicular to the line PQ. So you can see that this angle here is my right angle, right? That's my perpendicular. So there is my vector projection, right? And here is the intuitive idea here. Suppose that, well, let me make some room here before I start talking. So a projection is truly what you would think it would be. Imagine if you had, say, a light, and maybe, can I do it here? Can I make shadow puppets? Yeah, so we can make puppets on the whiteboard here. And so that's truly what a projection is. It is what you would get if you were to cast a light onto a system of vectors and say, where does one's shadow project? That's what a projection is. So intuition says the following. So let's shine a light down perpendicularly onto vector V. Right, so let me put my system back over here. So here's U. Let's do V in black. So there's V. This is U. And supposing my light source was up here, right? So there's light. And this guy is shining down perpendicular. So if this is flat with the ledge of the whiteboard, the light is coming down perpendicularly just like this, as an overhead light directly over top of the whiteboard would be what you would look at there, right? So you shine down this light, and what's going to happen to vector U? Vector U is going to cast this shadow. We'll cast a shadow onto the line through V. In other words, you shine down the light and you won't see, I mean, vector U will no longer look oriented off like this. In other words, if this is V parallel to the chalkboard, U is really like that. But if you shine down the light perpendicularly, the shadow is not going to go like this. It's going to go flat, parallel to the chalkboard ledge. That's the projection. So the projection, I guess I'm using red for projection. the projection is this shadow piece, right? So this is a proj sub v of u. And so this shadow is proj sub v of u, right? So have the light being cast down and forming this. And you notice, too, it makes sense. I mean, this is a relatively steep angle that it's projecting up. So here you're flat, and then you're going sort of steeply. So this is a lot shorter than u is, because the shadow is not going to come as far out as u did. It's going to stop when u is done. It'll no longer have a shadow being cast down once the tip of u is gone. Right? So that's why you have this much shortened projection versus the real vector u. And suppose, just for a minute here to get our bearings down some, what if we considered the other way around? So here we're projecting u onto v. What if we considered the alternative case, which is the projection of v onto u? Let me redraw my system down here. So there is u, and let's do v like that. All right. So now my light is being cast down perpendicularly to u. So if you kind of imagine taking a perpendicular, probably your line is something like this. So maybe your light source is something like that. That's reasonable, I guess. It's casting down perpendicularly onto that, right? Now you're going to have this vector over here be projected down as well. So now you can kind of imagine a reorienting. So maybe what's even better is if we shift this. Maybe let me redraw. So maybe if we shift it so that I can kind of put, so here's, let me draw u flatly. If I draw u flatly, then v kind of points out like that, right? So imagine just rotating this so that this now lies flat, parallel to the chalkboard ledge, right? And rotate v so it'll look like that. This angle is still obtuse. And so now it's kind of easy to see. Here's my light source casting down perpendicularly. What's going to happen? This is long and pretty steep, right? It's going to cast a shadow down, which is going to come down here and run like this, right? The shadow is going to run out here and be much shorter than this vector, much shorter because of the angle. So my projection now will be drop perpendicular, right? This is proj sub u of v. Notice the difference in notation. This was projection of u onto v. This is the projection of v onto u, right? And so that is how the projection there would look. Notice in both cases, though, the projection is certainly in line with u. And in both cases, too, the angle between u and v is obtuse, so the projection actually is going away from the way that u is pointing in this case. Okay? So that's the intuition behind vector projection. So you can, if you're sort of stuck on something, you can probably even sort of make this picture and get yourself righted rather quickly. Or even you could probably, I don't know, go home and try it with a lamp and some little objects and get yourself oriented to projections. That's not too bad. But what does it matter for us? Why spend a good deal of time talking about these things? For one thing, one application that makes a difference for us is effective force. So suppose u is a force vector, right? And recall that effective force is if I'm pulling something flatly along the floor, for example, but I'm dragging it in some other direction. Say I'm hauling it like a rope, and I'm pulling like this on a rope, and I'm pulling the box on the floor. Not all of my force going this direction is going to affect this movement. This movement wants to go like this, parallel. So I'm wasting some force. How much of my actual force am I getting on the box? That's effective force, the force in the direction you want the object to move, right? So if u is a force, proj sub v of u is effective force parallel to v, right? And so e.g., I gave this example just now. Let's make it on the board. So you say you drag a box some direction v using force u. So not necessarily parallel to v. Maybe you're dragging it some other way. The box is going like this, right? Proj u sub v is effective force in direction v. So here, for example, is the direction of v. So maybe it's going like that. And so maybe here is the box that you want to drag, and maybe you're dragging it like that. So there's u, right? And I've gone too far. So you're dragging it with some force going this direction. The effective force is going this direction, the direction of the box moving, right? It's the projection. So proj sub v of u. It's like that, right? And notice here, the projection was going in the direction of v. Why? The angle is acute, right? So the angle is acute. It makes sense. I mean, how do I say this without sounding foolish? But I mean, one would, if you want the box to move this way, you're not going to drag the box this way. It doesn't make any sense. Drag the box this way, the box will move this way, right? So the projection is opposite to the way you want it to move. If you drag the box this way, it'll move in this direction. Not entirely that direction. It'll have some wasted force. But the angle being acute will determine whether or not it is moving in the right direction. So proj sub v of u is opposite direction to v if theta is obtuse. That is to say over 90 degrees, between 90 and 180. Right? Okay, so let's talk about how we get this thing. It's, I think, clear to see what's happening with the geometry, but we want formulas to deal with actual vectors with numbers. So this is not so helpful yet, but let's take a look and see what the geometry can tell us about the formulas. Let me get rid of my lights here. So formula for projection, right? This is sort of the payoff, I think. Okay, so here is our standard drawing. There's u. Maybe v is out here, and let's put some points on here. Here's p. Here's s. Maybe v is way out here, and the. I guess I've been drawing v in black, haven't I? Let's keep that trend up. Okay, and then we'll drop the perpendicular, right? I guess I'm not going to go over it a third time in red, but there, better. Okay, so this is the projection vector here, right? So this is proj sub v of u. And so there's our angle, and I've drawn this to be acute, but the obtuse picture we'll see is no different. There's not much change at all there. We could take a look and see that cosine theta in this case is adjacent over hypotenuse, right? So it is length of the projection vector over length of u, right? So there's that idea, and this leads us to the length of the projection vector is cosine theta times the length of u. Okay, so here's the length of it. We're still not 100% good yet, but this is nice because we know something about cosine theta in terms of dot products, right? And how about the direction of it? Well, the direction of projection vector. In the case of the obtuse or the acute angle, the direction of the projection is the same direction as v, right? So it's going the same way. And obtuse, they go opposite directions, but it's nothing worse than putting a negative on this. It's not some other direction that's unrelated to v. It's always either v or the opposite of v. So remember, the direction vector is a unit vector by definition, right? So it's v over the length of v, it's a unit vector, right? This is length 1. And let me talk about the obtuse case over here. Let me leave that there. We'll move to the obtuse case. Again, the obtuse case just takes one little adjustment. So this is acute theta. Right? And how about obtuse theta? Here we have the identity cosine pi minus theta is negative cosine theta. This will help us out here. How so? Here's the picture. There's u. Now v goes off like that. Our angle theta is obtuse between the two of them. Right. There is the projection. Let's see if I got this pretty well on. Not bad. There's the projection, right, like that, right? And also this over here is, I haven't drawn it fully, but I'm trying to put too many caps on one marker. This out here is minus v, right? So in other words, from here to out here is minus v, so it includes this red stuff too. It's all minus v, right? And this angle here is pi minus theta, right? The whole angle is 180, so pi minus theta and theta, complementary angles there. So I have cosine pi minus theta equals minus cosine theta, right? And cosine of pi minus theta is again adjacent over hypotenuse, right? So again, this is length of the projection over length of u, right? So in this case, length of the projection is minus cosine theta times the length of u. Notice when theta is obtuse, this is negative, so this is still a length, still valid. It's not a negative number. It's negative of a negative, right? But so that changes, but then the direction also changes. The direction of proj v of u is now minus v over absolute value, or over magnitude of v, right? So notice there's a no negative over here and two negatives over here, so chances are we're going to get some cancellation here, and we do. They'll go away. So here is acute, here is obtuse. Let's see here. Let me leave the acute case, and let's erase the obtuse case. And then let's keep proceeding. So either way, whether it's two positives or two negatives, the same result comes out. So either way, the projection, right, ends up being, remember, you can write any vector as a product of its length and its direction, right? We learned that in the last section. Let's do that now. So length is u cosine theta, right? Direction is v over magnitude v. Okay, and again, if the two negatives are there, they cancel out. That's gone. Either case works out to be this way, right? So now let's see here. I'd like to multiply top and bottom by a length of v over a length of v. V is not 0, so that's okay. If v was 0, there's no projection onto it. You can't project onto a point. It doesn't make any sense. So I will multiply both top and bottom by length of v over length of v. So in the bottom now I get length of v, and then that's one big thing, and then times v over length of v. So there's my length of v over length of v piece I've inserted. Okay. This is the dot product, right? This is u dot v. This is u dot v. And then we have these two pieces of length, length squared, right? This is a scalar, right? Dot product over length squared is a scalar times v. Right? So this is going to be a vector in the direction of either v or minus v. It's a scalar times v. That will be a vector either in the direction of v or minus v. Okay. And actually, you could write this if you wanted to as v dot v down here, because we know that's one of the properties. So this could be said as u dot v over v dot v, but it doesn't make a difference really. Where am I here? This thing here, the length of the projection vector, right? It's length of u cosine theta, which is also u dot v over v, right? Because we just inserted that extra v in there and got that, right? This is what's called the scalar component of u in the direction of v, right? And it is denoted comp sub v of u. It's not a vector, right? It's a scalar, but it's the component, not the projection. So this is a comp sub u, or comp sub v of u, or a comp u sub v, something like that. And what is this? It is either the length or the negative of the length of the projection vector. It's either going to be the length or it's going to be the negative of the length. It's going to be the length in the case of acute theta and the negative of the length in the case of obtuse theta. Okay, so maybe let's do an example here briefly of this. So example, so let's find vector projection of minus 1 plus 2j, minus I plus 2j plus 2k onto 3i minus k, and the scalar component of u in direction of v. Okay. So we have formulas now. It's more or less a plug and chug issue, right? So this is u dot v over v squared, length of v squared, times v, right? U dot v is minus 3 plus 0 minus 2, that's minus 5. So this is minus 5. The length of v is root 10. Square it, you get 10. Right, so that's negative 1/2 v, right? Which if you want components, you can write as negative 3/2, 0, positive 1/2, right? And the scalar component is just u dot v over the length of v, which is negative 5 over root 10. This is negative, therefore it is the negative of the length of this thing. So it is negative length proj sub v of u. Right, so it's the negative of the length of that guy. So there's the projection. This is clearly an obtuse angle because we have something that's projecting onto negative v, and this is the component, the length of that projection down there. Okay, one more topic here for this section. It's work. We spent a good deal of time talking about work in Calc 2. We will revisit it again at the end of the course, but right now let's look at some sort of simple stuff with work. So work. Recall you have a force F moving an object a distance d, then W equals FD. There's your work, right? assuming F, D are in the same direction. In other words, at its simplest case, it's force times distance, as long as everybody's going the same direction. There's no wasted force. And in our case, though, I mean, we know right away that effective force is often a reality of life. There's going to be a difference, so how do we compensate for that? So suppose the force F is in one direction, and the object moves distance d in another direction. Right? Then the work performed by the effective force is our question. So what is work performed by effective force? I guess I should say in the direction of d. Right? So let's take a look at the picture here. Here's some force vector, and here is, say, this entire thing is distance d. Something like that, right? And say you're moving this sucker from P to Q. Well, effective force is a projection, right? So drop, right? There's proj sub d of F, right? In other words, the projection of F onto D, right? And we can get rid of this over here, I think. Let's see what work would be. So work is still the same because our forces are moving in a constant direction. Not the same direction, but they're not changing direction. There's no reason to have an integral here, for example. There's no alteration of the amount of force over time or things like that. So here, work is the amount of effective force times distance traveled, right? And all the other force is just wasted. It doesn't do any work. It doesn't actually do anything, right? So what is the amount of effective force? Well, it's the length of the projection vector, right? So this is length, this is proj sub d of F. Distance traveled is magnitude d. Let me make this look cleaner here. So there is the amount of effective force. There is the distance traveled, right? So you get this, right? There's an angle, theta, between F and D, right? Certainly assuming it's to be acute if this is going to move in the right direction. Cosine of theta is adjacent over hypotenuse, right? So another way of saying that is cosine theta equals length proj over length f. That means length proj is length f times cosine, right? So this is length f times cosine theta times length d. And lo and behold, that's a dot product. That's a dot product. That's f dot d, right? That's f dot d. So the work is very much like fd, only it's just a vector dot another vector. Excuse me. A brief example. Suppose you have a picture here. Here's a crate, and you're hauling the crate at an angle of 25 degrees. So the crate's on an incline itself, but it doesn't matter. And you're hauling a crate at an angle of 25 degrees. You're hauling it up 8 meters. So this is D, right? and this is F here, and this is the floor. So the floor, the ramp doesn't matter. This doesn't make a difference down here. Only this angle of actual pulling matters, right? It doesn't matter if you're pulling it up an incline or not. Work doesn't care. The length of D here is 8 meters. All right. Let's see here. You're pulling at a force of 200 newtons. So that's newtons there. And anything else I need to say? No. So your work is F dot D, which is exactly this, right? So it's 200 cosine 25 degrees times 8, and you wind up with 1450 Newton meters, which is the same thing as a joule. Okay, that's it.